All right, this is Physics 1A, the third hour for June 2nd. And we're now going to talk about pendulums. We're going to start off with what's called the simple pendulum. Is the word pendulum strange to anyone? Is it a word that people haven't seen before? I think I asked this question at some point in class when we were talking about this before. So, okay, it's a normal word. Or, Jasmine, do you mean no as in you don't know what it means? Okay, that's what I expected. Prior to physics, you hadn't heard this word before, right? That's also what I would expect, yeah. Okay, so it's a pretty simple idea. So you take basically you have some support point. So let's say you've got a ceiling right here, and to the ceiling you attach a string. You don't have any. Okay, thank you. I appreciate you saying that. Okay, so you take a string and you put a mass on the end of the string. So we have some mass down here. And you attach the string to some support at the top right here, and then you just let the string hang down, right? That's basically what a pendulum is, okay? It's just a string attached to a ball, suspended from some point, okay? If you have any hanging plants in your house, like a plant that's like hanging up somewhere, that would be an example of something that might exhibit the properties we're talking about. And what we'd like to understand here is what happens to this system when we displace it slightly from equilibrium. So this is our equilibrium position right here. Where the system is equilibrium. There's a tension that pulls up on it. There's a weight that pulls down, but they're balanced with each other, so the net force acting on this object is zero. An old school clock, like a grandfather clock, is something that works off this principle. A metronome is kind of similar, but it's kind of upside down. Just ball and a string. I don't think I have any string in my house where I would show you an example of this. But it's just like you hang something, and then you suspend it, and then you just... What we're going to do is we're just going to displace it a little bit and watch as it vibrates back and forth like this. That's pretty much it. So if we take this object and we displace it slightly from equilibrium so that it's hanging, like, let's say, like right here. Oh yeah, swing. Thank you, Chris. That's the much better example. Yeah, like a swing. Like when you go to a park and there's a swing. That's a pendulum. That's an example of a pendulum as well. And if you push someone in a swing, they swing back and forth and back and forth. Yep, great example. Okay, so in our case, we're going to say this is M. I'm going to define the length of my string to be L. And we're going to observe and look at the forces that are acting on this object. So if we pull this object to here, then the forces acting on it are going to be... Come on, let me click. There's going to be a weight that goes down, and there's going to be a tension on the cord that goes this way. So we've got tension, and we've got weight. And what we're going to do in this case is we're going to break these up into components, and our components are going to be such that we make an axis that goes this way. Okay, so we're going to kind of continue the direction that the string is pointing. We're going to make this be our axis, and we're going to call this the radial direction. So this is going to be the radial direction. And then the tangential direction will be the other direction that we care about here. So the other direction is going to be perpendicular to this, so it's going to be pointing like that. That's going to be the tangential direction. Oop. Click this one. Click. Wait, is it? Okay. Ooh, what is this doing? I don't know. So this will be our tangential direction. I don't need to make this so long. Should probably make a different color too. So that's our tangential direction then. And we'll break up mg into components. One component pointing along the tangential direction, and then one component pointing along this direction here. In order to do that, we need some angles. So let's call this angle made at the top here theta. The same angle here will be theta. which means that this component of the mg vector is going to be mg times the, sine of theta. And there'll be another component of mg that points in the radial direction that'll be mg cos theta. Like that. Probably should make this a little bit shorter, but probably okay. So this will be the component over here that's mg cos theta. And our mass is m, but that's looking kind of messy there, so I'm just going to get rid of that. So, as a result of this type of a breakup of the forces, what's going to happen now is that our object is going to kind of rotate or swing back and forth here, and its radial distance from this point is never going to change, which means that if I sum up the forces acting in the radial direction on this object, oh, OneNote just crashed. Okay. If I sum the forces in the radial direction on this object, they should be equal to the mass of the object times its radial acceleration. And if I sum the forces acting on the object in the tangential direction, that's this way, tangent to the path, then they should be equal to the mass of my object times the acceleration in the tangential direction. Let's focus just on the one on the right. There's only one force pointing in the tangential direction, and that's mg sine theta. So that means that mg times the sine of theta needs to be equal to m times a tangential. And the other thing that we can do is we can say, we learned before that tangential acceleration is related to the radius of the path that you're moving on, which in this case is going to be L. This object is basically going to swing back and forth like this along a kind of partially circular path whose radius is going to be L. So the tangential acceleration is going to be L, and then we multiply that times alpha, where alpha is the angular acceleration. So let's replace that inside of here. So we'll write mg times the sine of theta. Oh, we don't even need to write the m because that's actually gone away now. So we'll write m goes away. We just have g sine theta is equal to a tan, right? But as I said over here, the tangential acceleration is L times alpha. Okay. But now we got to start thinking about the sine of what I just wrote down. So we have g sine theta is equal to L times alpha, right? What direction would the angular acceleration be in this picture when the object is right here? Will the angular acceleration be to the right or to the left? To the right, right? So we call that positive or negative, you think, in this position? Is alpha positive or negative? It's positive, right? It's a good way to define it. Okay, let's make it positive. Okay, so alpha is positive, right? So if alpha is positive and it goes to the right, what about the angle? Is it positive or negative? The angle seems like it was defined that way, but the alpha is the other way, right? They're like opposite to each other, right? Like the angle opened this way, but alpha was back the other way, right? One of them is, let's see, theta is measured clockwise while alpha is measured counterclockwise, right? Does that seem right? It seems like theta is negative, right? Does everyone agree? If that's not super obvious, if we go to the other side, I think it maybe will be. If the object was over here and its acceleration was this way, right? Then I would say that alpha would be negative, but the angle would be measured this way, so theta would be positive. This looks like theta equal to theta, I just realized. I'm sorry about that. I just mean negative. Does that seem reasonable to everybody? That they're kind of opposite to each other? Alright. That means that we kind of need to throw a negative sign on our equation right here. So we'll put a negative sign in here, we'll put a negative sign in here, we'll put a negative sign in here. So our equation now is, and this is just because if theta is negative, alpha is positive. If theta is positive, alpha is negative. Okay. All right. Oh, by the way, mg sine theta in this case is the restoring force. So this means that this object is going to undergo simple harmonic motion because it has the two key components, which is an equilibrium position and a restoring force that always pushes the system back to equilibrium. In this case, that force is gravity. Okay, so we have negative g sine of theta equals L times alpha. Now, alpha and theta are related to each other, right? How is alpha related to theta? You need a derivative, right? Theta is the angular position. Alpha is the angular acceleration. So alpha is equal to the second derivative of theta with respect to t. Right? So if we put that into here, and then we do a little rearrangement here, oops. We get that. Why is mg sine theta negative? So it's not so much that this is negative. You know what? What I could do is this. I could do it like this. This may be a little clearer. It's that the angle is negative. The only reason for doing this, Joanne, is because when we get to this line right here, and we have theta and alpha that show up in the equation, both alpha and theta, because they're angular quantities, their positive and negative nature is determined by clockwise and counterclockwise, right? When we were doing rotational motion, you'd pick something. You'd say clockwise torque is positive and counterclockwise torque is negative, or whatever you want to pick, right? So when we measure the angle to the left, the angular acceleration is to the right. That's what's happening here. So if we pull the object this way, then theta is going to be, I'm calling it negative, and alpha is positive. Why is A tan equal to L alpha? This is something we derived in a previous chapter, Tombui. This is something we derived in a previous chapter. It comes from the idea that the tangential velocity would be equal to L times omega. L is like R. So yeah, we did this in a previous chapter, basically. If you want to go back and look at the notes. Okay, so here's our equation. Now, this is simple harmonic motion, but the problem is this sine theta that shows up right here. So if we compare this equation, I'll just copy it so we can put it side by side, and we go back to our derivation of what happened with the box on a spring. Let's put this right here. Notice that, I'll put it over here because it stands out a little more. Notice here that we can compare that equation to like this equation, for example, right here. In fact, let's just take them both, cut them, and put them back down where we were working. So if we compare these two equations here, they are very similar to each other in the sense that we have a function theta, we have a function x, there's a negative sign, there's the second derivative, and there's this quantity that shows up in front right here, right? They're very similar. The main difference is that this is a sine function as opposed to just x. And that makes this much trickier to solve in terms of a differential equation. So what we're going to do is we're going to force this to look like this by doing what's called the small angle approximation. So you're going to see this show up more than once in physics. We're going to use what's called the small angle approximation, which says that for angles that are small, okay, so basically for theta small, less than about 20 degrees, and it has to be in radians. So actually using 20 degrees is a bad example. 20 degrees is a small angle, right? In radians, that's 20 times pi over 9, or pi over 180. So about 0.345 radians. That may even be too big, honestly. But for theta less than or equal to about 0.35 radians, let's see if it's true for that number, actually. I'm just curious. It's going to be pretty close, probably. But yeah, it's pretty close. That sine theta is approximately equal to theta. For small angles, sine of theta is approximately equal to theta. You can test this yourself. You can try sine of 0.1. If you plug that into your calculator, what you're going to get, and it's got to be in radians, okay? Sine of 0.1 is 0.0998. That works, right? It looks like the sine of 0.1 is approximately equal to 0.1. Does that seem reasonable? Now, as the angle gets bigger and bigger, the approximation is going to get worse and worse, okay? So what we can say is the simple pendulum is going to act like simple harmonic motion as long as the angle doesn't get too big. If you took Physics 2A, you probably investigated this in a lab in Physics 2A at our school, where there's a pendulum lab, and they tell you to measure the period of the pendulum for various starting angles. So you started at 10 degrees, and you measure the period. And then you started at 20 degrees, and you measure the period. And you started at 30 degrees, and you measure the period. It's very time-consuming, all that kind of stuff. But what you usually find is after you get to an angle that's greater than about 20 to 30 degrees or so, that what I'm about to tell you isn't going to be true anymore, basically, okay? Because this is the reason why. We're making an assumption it's an approximation. Okay, we're approximating that sine theta is equal to theta so that we can come up with a result that's usable, because solving this differential equation is otherwise too challenging. So we're going to use this. We're going to let sine theta be equal to theta, and then our equation now is going to become negative g over L, but we're going to do the same thing we did last time. We're going to say let g over L be equal to omega squared. Do exactly the same thing. So this equation is going to become negative omega squared theta is equal to the second derivative of theta with respect to time. And now, when we compare this equation with this equation, they are basically the same equation. The difference being that in the case of the box on a spring, it's x. In the case of the simple pendulum, it's theta. Okay? We're running rapidly out of time here, so I'm going to cut to the chase. This means that the simple pendulum for small angles will exhibit simple harmonic motion, where the angular frequency now is going to be equal to the square root of g over L. And that also means that the period, which is equal to 2 pi divided by omega, is going to be equal to 2 pi times the square root of L over g. So the period of the pendulum is determined by two things: the length of the pendulum and gravity, right? Gravity. So, for example, if we choose L to be equal to 25 centimeters, okay, let's calculate what the period for the pendulum is going to be, all right? The period for the pendulum, if it's 25 centimeters, would be given by t is equal to 2 pi square root 0.25 meters divided by 9.8 meters per second squared. And the units will work out that you get t out of this. I think you're going to get an answer that's really close to 1 second if you do this. I got 1.003 seconds. And if you made it just a little bit shorter, it would have a period of exactly 1 second. So think about how powerful this is. If you take a cord that is exactly 25 centimeters long, right, and you suspend from that cord a mass, does the mass matter? Does the size of the mass matter? Nope. The mass does not matter. That's actually kind of surprising. But if you understand anything about the way gravity works, which you all kind of do now, right? you know that everything accelerates the same on the surface of the planet, no matter what its mass is, right? Gravity is constant. So it's just the fact that there is gravity that allows it to move back and forth. If you take a pendulum that has a length that's equal to 25 centimeters and you displace it slightly from equilibrium, 10 degrees, 20 degrees, 30 degrees, doesn't matter how far, then it will oscillate back and forth with a period of 1 second, which means that if you start it over here, it's going to go from here over to here and then back again in 1 second, right? You'll start here, you'll go, yeah. Yeah, it's pretty much just the length, right? Because we're not going to change the acceleration due to gravity. Are we? I don't know. Let's talk about that in a second. But the period is 1 second. So just think about how powerful this is. Such an object like this, you can use to tell time. Very accurately. You can use a pendulum like this to tell time out to about a few digits before it starts becoming. And of course, if you want to make it exactly 1 second, you just need to figure out what the value of the length needs to be, and you can shorten it. And so you can use this as a timepiece. That's why, as someone said earlier, old-timey clocks, or like grandfather clocks, which are the clocks that have the big metal, like, hanging thing inside of them, they tick time based on a pendulum that swings. And the cool thing is that even when the pendulum swings with smaller amplitudes, the period's not going to change. It's just not going to change. You can try this next time you go to a park or something with your nieces, nephews, friends, children, whatever. You can put a person on a swing. You can push them and make them swing back and forth and just let them go. And then you can time how long it takes for them to go through like 10 swings. And you can figure out if what I told you is true, that the period does not depend on the amplitude and it doesn't depend on the mass. So that's pendulums, and I'm going to leave it to you to solve problems with this because I do want to get on to summarizing this course, and yeah. So at larger angles, what is no longer true? This will no longer really be true. The period will change when you use larger angles, Joanne, basically. Yeah, I wasn't really clear about that, but thank you for asking that question. That's right. Yeah, the period will no longer be super accurate when you get to larger angles. Because we're kind of treating it as if it's not really moving in a curve. It's almost like it's moving back and forth like this, but there we go. So there is one more problem here. You'll see like one problem on your homework or two problems on your homework about pendulums. We could go through this problem, but I don't think it's super important. The one thing we're not going to have time to talk about is what's called the physical pendulum. So I will leave that for you to study for yourself, the physical pendulum, okay? And so what we'll do for the rest of the class now is I'm just going to go through like a general review of Physics 1A. I hope this is something that will be helpful to you. I don't necessarily know if you're going to find it particularly useful, but I've gotten a lot of questions about people wanting me to do this. If we were having a normal exam, I would absolutely always do this. Probably even spending a little bit more time, but I never really spend more than 30 minutes doing this. So we have about 20, and that should be more than enough to talk about this. So what have we studied this semester? We've studied physics, obviously, general physics and the basics of it, with the only limitation being that we can pretty much just use calculus. Is the only thing we can use, which allows you to do most of everything you need to do in physics. So you've learned, effectively, everything that you need to know about classical physics. And what are the things we learned? Well, we learned that there are fundamental concepts that describe the motion of objects, motion of rigid objects. Notice that we didn't talk about fluids in this class. We didn't talk about gases. We didn't talk about liquids. We didn't really talk about the motion of elementary particles either. What we talked about is the motion of large objects, baseballs and cars and people and boxes and things like this. And we learned the way that they behave comes down to, I would say, 4 fundamental concepts, okay? There are 4 fundamental concepts that tie together all of Physics 1A, and this is what they are. The first one are Newton's laws, basically. So, really, of these, the one that you use the most in this class is the second law, that the net force acting on a system is equal to the mass of the system multiplied by the acceleration of the system, right? Newton's laws. Now, there are special cases of this, right? And I would say there's basically 3 special cases, right? There's the case of equilibrium, which is the case in which the net force acting on the system is equal to 0 and the net torque acting on the system is equal to 0. That's a special case of this equation. There is the translational motion version of the equation, which is the one where you turn it into net force in the x direction is equal to max, and so on and so forth. Net force in the y direction is equal to may. And then the last piece of it is circular motion. And in circular motion, we basically say that the net force acting is equal to, well, mv squared over r, as long as you look at the forces acting in the radial direction, right? Okay. So Newton's laws break into these 3 basic ideas: equilibrium, translation, and circular motion, right? And you can use these to solve all types of different types of problems, right? But realistically, if you just remember this one equation and you remember what the acceleration is in equilibrium, it's 0, right? This is a equal to 0. This is just a equal to whatever ax or ay or whatever you happen to have. And this one is acceleration is equal to v squared over r. You realize that these are just 3 special cases of the general equation, which gives you less to memorize, less to understand, and less to think about, right? When do you use Newton's laws? Well, you use Newton's laws whenever you've got a system that has forces acting on it, and you know that there's going to be a constant acceleration. So usually you're using Newton's laws when the acceleration is constant, right? And combined within this idea of constant acceleration is one other small piece, and I always feel like this is overrepresented in terms of physics courses, but regardless, I mean, if you took any type of basic physics course in high school, if you took physics 2A at this school, you probably got a lot of kinematics problems, right? You notice in this course we didn't spend a lot of time on that stuff. We did 1 chapter on one-dimensional kinematics, 1 chapter on 2-dimensional kinematics, and 3-dimensional, but we didn't spend a lot of time on it, right? So this is a very small portion of physics, but keep in mind that kinematic equations only work with constant acceleration, and really, Newton's laws, all this stuff, almost always refer to constant acceleration. Now, Newton's laws can refer to systems in which the acceleration is not constant, but in physics 1A, that's not something you see very much, or at all, as far as I can think about it, right? Okay, a lot of details here, but the big thing is Newton's laws, one of the core kind of fundamental principles of physics 1A, okay? All right, second. In order, the next one that we learn is energy. And the big idea is conservation of mechanical energy. Or just, I usually just write it as conservation of energy. Okay? And within the idea of conservation of energy, there's a lot of different concepts, right? There's the concept of kinetic energy, which has 2 different forms. It's got the translational kinetic energy, which comes in the form of 1/2 mv squared, where you have to take the velocity of the center of mass. It comes in the form of rotational energy, which looks like 1/2 I omega squared. And I think that's it for this class, right? That's the only kind of kinetic energy we've talked about. You also have types of potential energy, right? You've got the potential energy due to gravity near the surface of the Earth, which is just mgy. You've got the potential energy due to the gravity in space, let's say, which is the one we learned about last week, which is negative big G m divided by r. And we've got the potential energy for springs, which is what one of the things we talked about today, 1/2 kx squared. So again, little tiny details, right, of a bigger concept, which is conservation of energy. Also contained with conservation of energy is the inherent connection between work and energy, right, which is that this is our general equation. WNC is equal to delta K plus delta U. This equation, much like F equals ma, is commonly a starting point for doing problems. This is something you should think about while you're working on your exam, is if you have a problem that involves energy, you almost certainly, when you're showing it to me in the during the final, if you're going to use this equation, start with this equation. This should be the first step. And not only that, but this is going to apply to your other physics classes as you go on, like, energy is going to keep showing up. It'll show up in 1B, 1C, and 1D. Energy is a concept that ties together really a lot of different concepts, because beyond the type of energy we talk about in this class, you're going to later learn about thermal energy, and you'll learn about electrical energy, and you'll learn about, if you go on in other classes, like you'll learn about chemical energy in your chemistry class. And energy is something that, it's a nice idea because it can connect different concepts, right? Like, you can have the energy coming from the sun, which is light energy, and we can convert it to electrical energy with a solar panel, and then we can take that electrical energy and we can use it to charge our the battery inside of an electric vehicle, and then we can take what was electrical energy, and we can now turn it into mechanical energy to make the car move and drive us around town and give us kinetic energy, right? It's just, energy is just a great concept like that. It's core to all of physics. If you study physics long enough, you'll realize that energy and matter are connected to each other through Einstein's equation, E equals mc squared, right? So it's a really important concept. And the cool thing is that even when you learn about other types of energy, you're still going to use the same energy equation. You're still going to use the same equation. So you might as well get comfortable starting from this equation, because you're going to keep using it over and over and over again. Now, in order to use the equation, sometimes you need to be able to calculate how work is done. So another kind of piece of this that you need to know is that, work done is equal to the integral of a force dot product with displacement. You usually don't need to do something so complicated in this class. If you have a constant force, then usually what happens is you just say work is equal to, force times displacement, right? Dot product between force and displacement. This is usually what you do in this class. Keeping in mind that work can be negative, like with friction, it can be positive, and it can be zero. If you have only conservative forces acting, which is like gravity and springs, then the work done by non-conservative forces can be zero, okay? Conservation of energy, fundamental idea in physics. And there we go. So that's the second big idea. All right. You want to guess what the next one I'm going to write down is? It's also a conservation law. What was the next conservation law we learned about after energy? Momentum, yeah. So the next idea is conservation of linear momentum. So another big idea in physics, when objects collide with each other, their momentum is conserved, even though their energy is not conserved. So this is a powerful concept in studying the collisions of bodies. It's also a powerful concept in just understanding how objects hit one another, like how a baseball hits a bat, or how a hammer hits a nail, or anything like that. And the big equation for this one is that if you look at a system and you want to understand how, what's going on, we have our impulse equation, right? That impulse which is usually equal to something like a force multiplied by a time interval is equal to the change in momentum for a system. And this is usually an external force that we're talking about here. Okay, right? But very commonly, this force there's no external forces acting on the system, which leads to conservation of momentum, which just tells you that the initial momentum of a system is equal to the final momentum of a system. And you can use this to solve all types of problems, as long as you remember how momentum is defined, which is just mass times velocity. And this will allow you to handle problems that involve collisions. One thing I could do as we're doing this is something I would normally do as well if we were in class. I'll do it at the end. I'll talk about when you use each of these ideas, okay? But for momentum, it's going to be collisions. I don't think there's anything else to say about linear momentum. It's a pretty simple concept in that regard, okay? And then the final one is the one conservation law I haven't mentioned, which is conservation of angular momentum. I guess in a way you could probably just merge these two into one idea. You could say momentum's conserved and then angular momentum, but they are very different, okay? So for angular momentum, the idea here is that we have this quantity L, which can be written as either I omega, or it can be written as L is equal to mvr times the sine of an angle, right? And both of these are useful. And what we know is that in a system, if there are no external torques, so when torque external equals 0, then the initial angular momentum of the system is equal to the final angular momentum of the system. And that's pretty much, that covers most of the things. One other thing is that a lot of these things are connected to each other through Newton's laws. Because another way you can write net force equation here is you can write net force is equal to the time rate of change of momentum. And actually, if you write it like this, then you realize that Newton's laws are really just a subset of momentum conservation, right? Because if you rearrange this equation, you basically get this equation. And there's a form of it down here, which I don't remember if we ever talked about in this class, which is that if you sum up all the torques on a system, it's equal to the time rate of change of the angular momentum. Somehow I don't think we got to this. Mostly because we ended up doing a bunch of different labs at the end that I wasn't planning on doing. But regardless. That's it. I know we studied a lot of stuff in this course, and I know, yeah, it's a complicated course. Physics 1A is really, really challenging. And I think that it can be extremely overwhelming as a student. You as a student, I'm sure many of you are very overwhelmed in preparing for even just doing one problem on the final. But that's it. Those four ideas are really all there is. The three conservation laws and Newton's laws. That's it. Every problem that you do on the final, for any of you, you're going to start from one of these points. You're going to start from here, here, this one, or this one. That has to be the starting point, It has to, because that's all we know. That's all we know about physics, is that these are the ideas that bind together classical mechanics. Basically, that's what we've been studying, is classical mechanics. The study of, I think this title's the title of this course is Physics 1A Mechanics of Solids, right? The core is energy. I think so, yeah. But it's not all there is, right? I will, Ton, after class, if that's okay with you. I'll help you with the question, yes. Yeah, we'll talk about that after class too, Hader, okay? Or Jazba. If you need extensions on any missed homework classes, you need to send me an email. Okay, so that covers the topics. Let me just mention some of the things that will tip you off on a given problem. This isn't as relevant because you're gonna get so much more. Like normally on a normal exam, you'd have like 5 to 6 problems that I would give, and you would have basically like 2 to 3 hours to solve the problems. And one of the things that people mess up when they have that kind of tight setup where you have to solve problems during a given time period is that they use the wrong rule. Like they use momentum conservation when they should have used energy conservation, or vice versa. Like they get a collision problem, but they use energy. So that's probably not going to be as much of a problem for all of you. So I don't know how relevant this is, but I'll just say over here that we use linear momentum conservation for collisions. We use Newton's laws for like objects moving on planes or objects moving along flat surfaces. We use conservation of energy for curved surfaces, like ramps that are curved, for things that are moving in like kind of a type of, whatever, curved path. Problems that have springs in them, you're almost always going to use conservation of energy. Conservation of angular momentum is usually going to involve like some kind of either angular collision where you have like a bar. I'm just going to say angular collision because that's usually what these are used for. Yeah. But then, a lot of the problems that you can see are going to have like, multiple pieces, right? Is there any scenario in which energy is conserved during a collision? Yes. Elastic collisions are collisions in which energy is conserved. Yes. And that occurs when you have a collision between like two magnets or a collision between two fundamental particles, collisions in which two objects don't really touch each other, basically. And you were thinking that the final problem... Yeah, I mean, the problems that you get for the final are going to cover multiple topics that I'm listing here, right? For sure. But because I have to write I have to write a lot of problems. I think for the first test I wrote, I think it was 14 or 15 problems, basically. And I kind of split them up between the classes. I think, like, 7 of them would go to half the class, and the other 7 would go to the other half of the class, basically. So some people got the same problem, but it's hard to come up with problems, Angie, where like everybody's going to get tested on every single one of these ideas. That's really challenging to do. So it's usually going to involve like 2 or 3, basically. It's exactly the same as the last midterm. Yeah, it's not going to be like we're not. Yeah, I don't think you're going to be surprised. I don't think you're going to be surprised by what you see. The biggest thing that I can say in prepping for the final that's relevant for this online thing, and I hope to God this is the last time we ever have to do this, is just practice. That's all I can say. You have 3 hours. It is a massively substantial portion of your grade that you're being evaluated on. You want to get as many points as you possibly can. So, the best ways to prepare are to try a lot of problems. I mean, just do physics problems. And when you do them, you have to do them in a way... Okay, I'm not even going to say that. Point is, just do physics problems. Challenge yourself. Do problems that are hard. Or at least kind of difficult. If you look at a problem and you kind of know how to solve it, you could be like, hey, I think what I'll do is like think about this, but don't spend too much time on it. You want to spend time on the problems that are hard. The other thing is, once you've gotten your problem, so on like next Monday or Wednesday, depending on when you get your problem, once you have gotten your problem, you need to set aside those 3 hours, or at least as much of it as you can, to doing the problem once, and then throw away your work, do it again, throw away your work, do it again. Make sure you know the problem really well, however, whatever works for you. And then what I would do is I would find someone to try to present the problem to. I would find someone, they don't have to know anything about physics, just someone to talk to, or go to the mirror and explain it to yourself in the mirror. Or just do something where you have to actively, out loud, explain everything, right? And, this could be, you could get like, a parent, you could get a sibling, have them sit next to you, put your piece of paper down, and just start explaining it, okay? And just have them sit there and listen, so that you're forced to actually explain it out loud, and time yourself, okay? Because you want to finish within like 10 minutes. If you go over time, I'm definitely going to dock you some points. I'm not going to dock a lot, but if you take like 20 plus minutes to solve the problem, it is definitely going to drastically affect your grade, because you're when you do stuff like that, you're effectively reducing the time that I can give to other people, because I have a limited time that I can see everyone, right? And so we have to be fair with the amount of time that we give to everyone. If I allow one person 20 minutes and I allow someone else 10 minutes, that just isn't fair. It just flat out is not a fair and equitable situation. Everybody deserves. Now, if you need more time on exams because you're allotted more time on exams, that is a completely different story, and I can give you more time, right? But when we have to get through 60 people, 30 people on Monday and 30 people on Tuesday, you got to get it done in a reasonable amount of time. All right, it's already 5:10, so I have to probably stop. That's the best advice I can give to all of you. And I really hope you're all very successful. I'm not here to punish anyone. I'm not here to reward anyone. I'm here to hopefully give you some kind of physics education during this unique situation of the lockdown, and hopefully, I don't know, hopefully you've all learned some things. I'm doing what I can to get through this process, and I know for a fact that I could have done a better job if we were in person, but we're not, so I'm doing what works for me, and I hope you're all well prepared, and I hope that you all do really well on the final. I really do. I'll try to be fair in evaluating you, but that doesn't mean I'm going to be easy in evaluating you. So show up prepared, please. Please, for God's sake, show up prepared. Yeah. Probably, Angie. If you went on Wednesday last time, probably you'll be going at the same time. There have been quite a few drops. And thank you, Miguel, for saying that. But also, I want to say thank you to all of you for sticking through this semester with me and putting up with my personality and the fact that sometimes I am not as kind as I should be, and I apologize for that. Yeah, I think I could have been a little bit nicer to you all in general this semester. It's really hard when I can't see anyone. It's really hard when, all I have to work with is the Discord chat and stuff like that to continue to act in a way that is proper and respectful to each of you as human beings. And so I apologize for the times that I might have failed in that regard. But anyway, I hope you all succeed. I hope you all succeed in your future physics courses. And I hope you all, once you're done with the silliness that is college, do great in your personal lives as you go on for whatever career that you choose. And I just hope you all do great. I really do. Good luck on all the transferring and the rest of your physics classes and the rest of your stuff. And yeah, this fall, if you are happening to take a class with me in the fall, or you happen to be on campus in the fall, and you want to stop by and say hi or something like that, or have any questions about anything, I think we will be on campus for a pretty sizable amount of time. If you're taking 1B or 1C with me in the fall, I know we are having labs on campus, which is great. And I hope that we can do exams on campus too, so we can just have normal exams again. But anyway, I've enjoyed this class. I will say, no matter what, I really do enjoy sitting down in front of my computer and talking to you about physics. I hope that that showed in some of the energy that I had for some of the topics. I know sometimes I'm talking about something and I explain too much, or I say too much, or I go off on a tangent, but everyone has their own personal style, and I guess that's my style. And I have enjoyed sitting around and talking to physics with all of you. I appreciate everybody that asked questions in the chat. Everybody that was involved, which I think that in general, I think most of you have been pretty involved in answering questions and stuff like that. Thanks, Joanne. I appreciate that. But yeah, just thanks for being involved, and good luck on the final. Just take it seriously. You're all capable of doing really well, and yep, you're all capable of doing really well. So do your best. I'm gonna put an assignment up on Mastering Physics. Not Mastering Physics, sorry. I'm gonna put an assignment up on Canvas, because there's still a couple labs we didn't do, but I'm gonna make it an optional assignment. We're gonna call it like summer homework is what we're gonna call it. There's a lab on log plots that you really need to understand in order to help out with Physics 1B. And I think probably what will happen is when we go back in the fall, if you take Physics 1B with me, we're just going to do the lab in person. But I'm going to leave it as an optional homework assignment. You don't need to turn anything in or anything like that. I'm just going to kind of direct you to what you need to do, and it's just kind of the thing that you need to do if you want to prep for 1B for the fall, basically. So. I'm not going to assign another lab. Well, I am basically, Chase, but I'm not. It's not going to be something you're going to turn in. Okay. I thought about doing it as extra credit, but I don't think that really is going to make much sense at this point. Yeah, I thought about that, Hudson, but I don't know how to do it. I don't know how to make it, because it's a lab. It's not a homework assignment. You know what I mean? It's a lab. That's the problem. It's not really a homework assignment. Okay, so I'm going to stop the stream, and then I'm going to start answering like the individual questions you guys have. I'll stick around for however long you want. I can't stay past 6. There is a class here at 6, but I'll stick around for as long as needed to answer questions, and we'll start with your question, Ton, about the R omega thing on that one problem. All right, so thanks, and see y'all next week.